Question 1. Search drums are often used for temporary storage of gases. The inlet and outlet molar flow rates are Qi and Q respectively. Develop the dynamic and steady state models of the system. So the search drums are shown as below, and the Qi and Q are shown. So first step is we have to make assumptions for the system. Since the question states that we are storing gas, so we have to assume that the gas is ideal. So we can bear in mind that for ideal gas, the formula is PV equal to nRT. Also, there is no temperature change that is given, so we can assume that the system is in isothermal. And the gases, they are not mentioned any particular gas, so we can assume that we only use one type of gas. Then the molecular mass is constant, and also we can assume that the volume is constant. Next, we have to determine which type of balance we have to choose. There is mass balance, energy balance, and also component balance. Since there is no temperature difference, there is no energy balance, and also since there is no component change, so there is no component balance. Then we have to solve for mass balance. So the general formula for mass balance is dm over dt equal to wi minus w. The m is the molecular mass of the gas, equals to the mass flow rate of the initial inlet minus the mass flow rate of outlet. Since it is gases, so we have to solve it in terms of moles, in terms of number of moles. So mn is equal to dmn over dt is equal to mqi minus mq. Q is the molar volumetric flow rate in minus molecular flow rate of out. So we have to simplify, since the m is the same, so we can factorize it. Then we can simplify it by just cancelling out the molecular mass. Then the equation remains as dn over dt equal to qi minus q. Since we assume that it is ideal gas, so we change the mole to be dpv over rt over dt equals to qi minus q. Since assumptions 2 and 4, which is constant volume and temperature, so we can put the volume and the temperature outside, and we maintain the P inside. So the equation is V over RT times the dP over dt equal to Qi minus Q. Then we move the V over RT to the other side. Then we have dP over dt equal to RT over V times Qi minus Q. So this is for the dynamic model. For the steady state model, we just simply put a bar on top of the variables. So dP bar over dt equal to RT over V times Qi bar minus Q bar. So for the dynamic model, we have to label the process variable, manipulated variable, disturbance variable, and also control variables until degree of freedom. So for process variable, firstly we have to determine what is the manipulated variable. So the manipulated variable is Q because, as we can see from the question, we change the valve here, so this is the manipulated variable. Hence, the Qi is the disturbance variable. For the process variable, we know that we only change P. We want P.
Is the control variable.
P is the control variable. Okay. For output variable, the control variable is P, the parameters is R, T and V, and we also have to measure the degree of freedom. Degree of freedom is the variable minus the equations. So since there are three variables, which is P, Qi and Q, so we have 3 minus the equation. We only have one equation, so the degree of freedom is 2. So the degree of freedom needs to be 0 to be exactly specified, so that we can solve the question. So the 2 comes from the manipulated variable, which is determined by controller, and the disturbance variable, which is determined by surrounding.
So that's all. For the question 2, as you can see here, okay, consider a constant hold up CSTR with volume of 46 meter cube, and the flow rate of the reactant and its concentration at steady state are 2.4 meter cube per minute and 8.01 kilomole per meter cube respectively. Okay, the reaction temperature should be maintained at 350, and we should develop the linearized model of this component balance and also the equation of the dynamic model in the deviation variable form. Okay, so additional data given in the question is about this KO and E and this R, which is the gas constant. Okay, so first we need to start with the mass balance. So dm over dt equals to wi minus w. So this mass is equivalent to density times volume. So this wi will be equivalent to density times this qi. Okay, so since density initial density is equivalent to the density, so we can cancel the density, ending up with dv over dt equals to qi minus q. Okay, so since in the question they state that it's a constant hold up, so therefore qi minus q will be 0, which means that qi equals to q. For the component balance, okay, dNA over NT will be equal to dCV over dt. So Na will be the number of moles and Ca will be the concentration and V will be the volume. So which is equivalent to CAI and times by QI minus CAQ minus RV. Okay, so since from previous page, constant OLAP, which is QI equals to Q, so we can make it this QI is equivalent to Q. And next step is to to divide everything by V. So which means we will only get dCA over dt, and here will be divided by V, and here the V will be missing. So this is the last one. And okay, then since it's a first order, so R will be equivalent to KOE to the power of negative E over RT and CA. So dCA over dt, so from previous just replace the R with this one. So our dynamic model will be exactly the same thing. But okay, bear in mind that this is non-linear term, so we need to linearize. Okay, so we move on to how to linearize this part. Okay, so the part that we need to linearize is actually this part. Okay, so now what is the variable? So the variable is not only one, but there's two variable, which is the t and also the ca. Okay, let's say we only take of ca as the variable, so that means it's already linearized, because the exponential only is making the term to be non-linearized, I mean to be non-linearized. So this we have to use of the Taylor series expansion. So firstly, fx bar will be the linearized, I mean non-linearized term. Okay, so the function of dx, df over dx, this is in terms of only t, only one term, and this is for this another term, which is the ca. So finally we'll be ending up on e to the power of negative e over r t bar and ca bar plus then this is the differential of the in terms of t, and this is the in terms of ca. Okay, so next, mm, next this is the dynamic model of this question. So next we have to this one for steady state model. So steady state model will be this thing. So how to get our deviation is actually dynamic model minus the steady state model to get our deviation. So and actually we no need to substitute any value of this ko, e and r, because in this question they actually only stated that just the equation of the dynamic model. That's all.
Hi, good evening. I am Nida Hong from Chemical Engineering Group 3, and now I would like to discuss about how I actually solve the question from the PIC video modeling question number 3. So here is the problem statement here. A processed liquid is continuously fed into a perfectly mixed tank in which it is heated by a coil of condensing steam. So here they say that the feed rate is 25,000 kg per hour of the liquid with a constant density of 800 kg per meter cube, and its heat capacity is 0.5 kilocalories per kilogram degree Celsius. And also they state that the hold up in the tank is constant at 2080 kg of the liquid. And now they state the condition, the inlet feed temperature is 30 degrees Celsius, whereas the saturated steam is 150 degrees Celsius to heat up the processed liquid. So at the initial steady state, the tank temperature is 90 degrees Celsius. So I have to derive a mathematical model of the system. So first of all, what I did was to draw a simple block diagram here so that it makes me easier understand and I can solve the question easily. So after that, the next step I did was to make assumptions. So in this case, I had made 3 assumptions, which is the first one, the system is the perfectly mixing, and the second one is the density of the liquid system is constant, and the last one is the heat loss is negligible. And these 3 are the most basic that we have to assume to solve this question. And then the next step is the balancing. So there are 3 main balancing here. So the total mass balance, component balance, and energy balance. And since the question state about it is a process liquid system, therefore we don't need to do the component balance. So the left over here will be the total mass balance and the energy balance. So first of all, let's focus on the total mass balance here. So what I did was to take the overall changing in mass per unit time. So we know that the change of mass is actually the product of density of liquid and the volume of the liquid. So I put it in a derivative from here. So it's d rho v over dt equal to the mass flow rate of inlet minus mass flow rate of outlet. So since we know that the density is constant, so we can factorize it out. We can move the rho here out of the derivative, which become this equation: rho dv over dt equal to the mass flow rate inlet minus mass flow rate of outlet. So this is my first equation. So the next step I did was the energy balance. So the concept here is exactly same as the mass balance up there. So the overall changing of energy in this system will be equal to the energy in inlet minus energy at outlet plus the external energy. So in this case, the energy is added onto the system, therefore it's a plus Q. So we know that for liquid system here, du dt is actually equal to dH over dt. So we can change this formula here into this form: dH over dt equal to W1H1 minus WH plus Q. Here is my equation 2. So the next thing I did was, I know that H is actually equal to M times Cp times delta T, and M here actually is the density times volume. So I make it into this form, which is rho v Cp delta T. So if I sub this whole thing back into equation 2, I can get this: d rho v Cp T minus T reference. And here goes the same for the right hand side of the equation. So for this step, I have to remind you all that the delta T is actually the difference between the specific temperature minus your reference temperature. Your reference temperature can be any value, because in the end they will cancel off each other. But easier for you, I always assume the T reference as 0. It's easier for me to solve the problem. Alright, so the next step here is, I know that the density, rho, and Cp are always constant in this system. So same I did to the mass balance here. I move up the density and the Cp, and here I get this equation here, the equation 8. So if you notice that the left hand side of the equation here, I actually can use the product rule to expand it. So the product rule of differentiation is uv prime plus vu prime. So if you apply this concept into this left hand side of the equation, you can get the equation number 4 exactly the same. So now you substitute the equation 4 here back into the equation 3, and you can get this whole complicated equation. So from equation 1, just now we know that the rho dv dt equal to W1 minus W. So we put this equation, substitute it back into this equation to replace the rho and dv dt here. Can you see the difference? The same thing exactly here. So we can solve this to replace rho and dv dt, and I can get this equation. So here is the complicated equation here. So what you need to do from here is use to expand and rearranging all the variables here, and finally you can get the equation something like this, exactly the same. And so because I'm actually finding the mathematical equation, mathematical equation, so I am focusing on derivative dt over dt, which is the change of temperature over the time. So I move this whole thing, the rho CPV, divided in left hand side and also right hand side, and I can get this equation. And this equation is exactly the mathematical model of my system. So here is the final answer, and thank you very much, and this is the ending of my part. Thank you and have a good day.